Hi, good afternoon. My name is Leon, and the paper I'm presenting is ONOIMA-RAN, breaking into an ORAN 5G indoor base station. So a quick motivation of what this is: we have an adversary here down in the left bottom corner who will attempt to get a hold of an indoor base station to, from there, attack either user equipments or escalate within the RAN. And today I've got the impression that you all are pretty familiar with breaking into stuff, but I was figuring I'll tell you a bit about the cellular network. So that's going to be my background to start this talk. You are typically users using your cellular data on your mobile phone to connect to the internet. And this happens by using the critical infrastructure of the radio access network, which is the RAN, that connects your phone to the mobile network operator's core network. There, authentication is handled, session management, all kind of control plane packets are taken care of, and finally your traffic will be transmitted to the internet. The ORAN, in comparison to the RAN, is the open radio access network, and basically, there's three things to know about ORAN. First, as you can see on the right side, the typical base stations are split into three components. From top to bottom, you see the central unit, the distributed unit, and the radio unit. We'll focus on the radio unit today, and that's basically the lower layers that are handled there. Then, via a fiber connection, traffic is sent on to the distributed unit that handles the middle layers, and these DUs and CUs are typically virtualized and deployed on servers. So that helps for scalability, and that also leads to the fact that only the radio units are deployed on the cell side, where in non-ORAN networks, the entire base station that's more costly is still deployed. So the thing about the open and ORAN is that it's not open source, but it's only open interfaces. So these two interfaces marked in blue arrows are very well defined in the standards, but what happens within these units is proprietary most of the time. And that's the first motivation of an attacker trying to get a hold of a radio unit to just see what's going on inside. However, moving on to indoor base stations in comparison especially to outdoor base stations. So why do we need them? Well, each generation of the cellular network just promises faster speeds, and the current approach here is to switch to millimeter waves, which is just a higher frequency band, which also comes with like a smaller wavelength, and these typically have less penetration, and that doesn't go well with like solid walls. So we really need indoor base stations in the future to just maintain connectivity within buildings. And this small little equation on the right side, indoor base stations equals indoor radio units, is just that in the context of ORAN, base stations are radio units, so we are focusing on indoor radio units, even though the title is indoor base stations. So why is this relevant? A quick motivation here. One of the German mobile network operators just recently in May rolled out an entire stadium just in time for the Euro 24, that it's soccer in Germany. And it was a really big deal because they achieved like a lot of traffic records within this tournament. And all of that happened on ORAN technology. So they really deployed ORAN there. They also deployed indoor base stations, as you can see on the picture here. So introducing first the system model we are looking at, and then the adversary model in more detail. The things marked in yellow here are the cellular network parts that the conventional RANs have. So it's G-node Bs, which is the current term for base stations, and these connect immediately to the core network. That's the cloud on the top right side. In comparison to that, you can observe that the radio unit, they are connected to the distributed units, as explained earlier, which then go to the CU, then to the core, and from there to the internet. And in ORAN, there is also a so-called SMO, which is the service management and orchestration platform. Simplify, this is where artificial intelligence is supposed to happen. That's currently in development, but it's also another part that is connected to all of the ORAN parts. So there's also a direct connection from the RU to the SMO. Just a quick summary of why indoor radio units are especially interesting to adversaries. Well, physical access control is just so much harder to achieve for indoor base stations. The mobile network operators usually have huge fences to put around outdoor base stations. They have all kinds of policies in place, but it's just so hard when indoor base stations are deployed very similar to enterprise Wi-Fi routers. It's just harder to achieve physical access control. Also, they are highly connected within the ORAN in comparison to the conventional RAN. And due to the open interfaces in ORAN, there's currently multiple vendors already offering ORAN radio units, and the number is just increasing. So with more vendor diversity, there just comes more bugs, and that's always worth looking into. So in more detail about the threat model. So on the right side, you can see the radio unit that we have investigated for this paper. It's from Airspan, and it's an Air Velocity 2700. Basically, we thought of what changes from outdoor to indoor base stations and what future adversaries might possibly be able to do. And we derived 4 capability classes from that. That is C1, where an adversary just has Ethernet access to the RU. These basically translate to the blue parts you can see here. So it's the 2 Ethernet interfaces on the bottom. And this can already be achieved by having access to a nearby adjacent Ethernet port that is, by chance, just connected to this radio unit. Escalating it even more, I will just quickly summarize C2 and C3 and C4, because for this paper we focused on the C1 capability. Basically, in addition to the Ethernet access, the adversary might also be able to achieve just like physical access to the radio unit, and that would also yield access to the power socket and to the magic HDMI debug port on top. If the adversary is on top also able to steal the RU, he can just take it home, do more thorough analysis, and potentially learn stuff and apply that to another radio unit deployed in the same building, for example. Or C4, assuming the adversary might also be able to redeploy the RU. That is just even more powerful because they can then insert a modified RU within a running ORAN. However, as already mentioned, we will focus on C1, and that is just because most of the other capabilities are just so powerful. For example, having access to the power socket just gives you an, trivial denial of service. And the debug port, it is HDMI. We have our suspicions of what's implemented there, but this is also a very powerful interface to have. So we assumed an adversary having C1 being able to connect to the RU via Ethernet. And this is basically what we found. So you see these ports, and these are the protocols and the ports that were open. We tried and found 2 of them being authenticated, so we couldn't do a lot there. However, there were some that were unauthenticated, and we looked at these more closely, also finding that the Mosquito port yields some magic management daemons. Just like quickly introducing these because they will be discussed in more details later. A quick summary of these ports. So the FTP port probably is intended for file uploads. We're assuming it has to do with the firmware. We couldn't really confirm that because it's broken. So we just couldn't upload files. They were mishandling an argument, and it broke. So we're still assuming it's for file uploads. The SSH daemon is actually intended by the ORAN standards, which is part of the management plane here, and it will be later used for netconf and like a form of authentication for netconf. However, it also provides shell access to the radio unit, which is not intended by the standards and can potentially become a problem. The telnet by itself is fine. It's not really considered in the standard, so it has no official purpose, let's say, but it's just there. It doesn't really do a lot, but assuming it will be connected to the management plane in some way, that then yields a direct violation of the standards because Telnet is not encrypted, so there is a breach of the end-to-end security here. The mosquito daemon is there to expose the management daemons to the outside world. Outside world in this context means the ORAN, so it's probably intended for the distributed unit or the SMO to just put commands into the RU. Therefore, there's also the net-to-peer, the netconf implementing here. That is just a Yang store of all the functions. And finally, the sysrepo agent that can catch these RPCs to really forward them to the daemons. Well, so we just decided to look at these protocols and just see what we can break into this radio unit. This is all observable from the outside without any, it's just like nmapping and just seeing what's there. So we first decided to look at this TCF agent. The TCF is the target communication framework. It's actually from Eclipse, and it's meant to communicate to built-in FPGAs in embedded systems. At least it has other purposes, but in this scenario, there's FPGAs on the RU, and they are meant to be communicated to by the TCF. We learned about the TCF agent because it just conveniently broadcasts on port 1534 periodically, and when looking at this packet, we found, okay, it tells you the host, the port, it's fine. It also discloses the operating system, and then we found that it says username equals root. Got us curious. Well, it's basically exposing a root terminal because it's just meant for developers to, to just execute commands on the RU. So that's intended, but leaving it before deploying it is a security hazard. So that first finding here gives us a root shell access to the RU. Next, we focused on the Sealish agent. That's actually a more convenient way of accessing the configuration of the radio unit. It's custom written, but it just does everything that is mandated in the standard. And you can, with this Sealish agent, just restart the RU. You can set vital parameters like the alarm temperature, and you can modify stuff that also affects the users, for example, the sending power. So I'll just quickly summarize. This is just a security problem. You can reconfigure the RU. You can potentially, this can lead to denial of services and can also affect users. Now, as I promised, the mosquito exposes the management daemons, and we closely looked at these. We found that most of them are probably written in C, and they had a lot of memory corruption vulnerabilities here. So I'm not sure how well you can read the code, but the important part is that there is fortified functions as well as unfortified functions in use. And these fortified functions basically check what the parameter length is, and if it's too long, it will just crash the daemon, which we could abuse to achieve a denial of service for these management daemons. And also we found like an unfortified function that we are pretty positive can be exploited to a remote code execution, but we didn't do it. However, we found another remote code execution that is a command injection vulnerability where we found an adversary control string input that, after looking into what's possible, yields 5 usable bytes to the adversary, and we managed to show that this can be exploited to a remote code execution. So also, finding 4 gives you basically full control of the radio unit because these the commands are forwarded to the operating system, executed as root, so that's full control. Yes. Why is this a problem? So what's the impact on the cellular network if an adversary really gains full control over RU? Well, besides the reconfiguration, denial of services, the next things that the adversary might face are the users via the, for example, broadband interface. They might also try to escalate like in the direction of the core network. So the next step would be the distributed unit. From there, potentially escalating the central unit and so on. Or they might go to the place where AI happens and attack the SMO. Yeah, so to sum it up, this figure summarizes everything we discussed in our paper. Just quickly going over it from left to right, we distinguish these different capabilities within our new adversary model for indoor base stations. We discussed what you can do with the interfaces on the RU. The HDMI debug port is something for future work. And also we didn't closely look into hardware interactions that are possible when stealing the RU to learn stuff, to maybe extract secrets. Right. Then there were some places where we found deviations from the Open RAN M-plane standards. I just briefly talked about that. It's in more detail in the paper, but on the bottom in the orange boxes, there are the findings. So 2 of them gave us full control of the RU. There's another finding where we assume a remote code execution is possible, but you can basically conduct denial of service attacks and you can reconfigure the RU, which is critical here. So what's the takeaway? Well, we didn't really do a lot of magic here. We just assumed this base station to be an embedded system and saw what we could do. However, base stations are part of critical infrastructure, and a lot of the stuff that we found is just easily fixable. For example, just not deploying the TCF agent. And for critical infrastructure, we should really ensure that these embedded systems are safe and secure. So that concludes my talk. Thanks.